heat of formation. Now, what is heat of formation? It is the amount of energy absorbed or released when 1 mole of a substance is formed. However, it's formed from its constituent elements. And these elements must be at SATP, standard atmospheric temperature and pressure. So at 25 degrees Celsius, 100 kilopascals of pressure. Hence why these are set at 0. So these elements here, these are going to be set at 0, and we're going to look at a few practice problems for you to understand what I mean by that, okay? Why they're arbitrarily set at 0, because this is our reference point. Next we have here our amount of energy. This amount of energy that's absorbed or released should be quite familiar by now. This sounds like it's Q, right? The amount of heat gained or absorbed. So we also derived that Q is the same as the energy transfer. And if you have no idea what I'm talking about here, please see my previous videos about enthalpy and specific heat capacity so that you can get a better understanding of this. But the amount of energy absorbed or released is also equivalent to the change in enthalpy, or the energy transfer. Now, a simple formula that we're going to be using to be doing our questions accordingly is our delta H. Okay, it's going to be a standard, and it's going to be standard molar enthalpy of reaction. So it's going to be an R or reaction. It's up to you. I like to use R, and it's going to be equal to the delta HF. So the enthalpy of formation, and it's going to be a standard as well, of the products, and we have to subtract it by the delta HF, so the standard molar enthalpy of formation, but of the reactants. And we have to emphasize here that if we're doing delta HR, this is obviously going to be per mole of a substance, right? So this one here is going to be certain energy amount of in kilojoules, and it has to be per mole of a substance because we are using R. Remember how we used to have this formula, delta H is equal to N times delta HR, because we have the amount of moles in question that we have to multiply with this one, because this one is in kilojoules per mole. So if you have the amount of moles here and the amount of moles here, diagonally they cancel out, so you're just left with the kilojoules. Okay, so this amount of kilojoules that we have for our delta H is not what we're seeing here. What we're seeing here is this one over here, the delta HR. So if we are going to get a value that is simply just kilojoules at the end of the answer, these must also do the same, because all of these here are standard molar enthalpy, right? Standard molar enthalpy here of formation, that's obviously per mole. Standard molar enthalpy of formation is per mole, just by the name of it, standard molar enthalpy, molar for mole, and this one here as well. So we have to multiply by the amount of moles in question, depending on the thermochemical equation that is given to us, and then we can eventually get our value here in just kilojoules. Let me do a few questions, and it should start making a lot more sense. Let's try to solve this question here. We have a complete combustion and given a thermochemical equation there, and then there's another possible reaction if it was done incomplete. Determine the amount of energy lost per mole if we did it this way. So rather than our goal of having complete combustion, because most of the time our goal is to get complete combustion, it's a lot cleaner, but if we end up getting incomplete combustion as written, so this is what we're going to be referencing first, and they give us the standard molar enthalpy of formation for C6H14, our hexane. Determine the amount of energy lost per mole. So the amount of energy lost is wasted energy. We got to figure out how much we lost because we couldn't achieve our complete combustion here. Let's give this a try. Let's first write out our formula, and then we can start solving this. Now what we need to do is substitute our values needed, but remember this is HR. This isn't just delta H. So this is going to be per mole of a substance. As you can see, hexane is the one in question because that's the one that's being combusted here. But there's only 1 mole of it anyway, so you're just going to multiply by 1. It's fine, it's already going to be done. So this is, again, per mole, but there's only 1 mole of hexane anyway, so you're just going to multiply by 1 mole over here. They cancel out, and you're going to be getting that value, okay, for the hexane. And we can do the same thing for these ones then, because if we do it for this one, these ones must also follow suit. So all of here, let's write it out, our delta HF of the products. This here is our first product, so we have CO2. So we have how many moles of it? We have 1 mole of CO2. And we have to multiply it by a kilojoule per mole, the molar enthalpy of the CO2. Where can we find it? Well, we just look at CO2 over here, our carbon dioxide, and as you can see, it's negative 393.5. I'm going to multiply by negative 393.5. This is going to be kilojoules per mole. And then eventually these are going to cancel out just like how this side did. So we can get a clean kilojoule number at the very, very end. I'm just going to put this in brackets over here because we got a lot more to do. We also got to do CO as well. So I'm going to add it with CO. I'm going to look for CO over here as well. And I see CO right over there. And CO is negative 110.5. So again, how many moles of that are there? Well, we have 1 mole. So I'm going to multiply by 1 mole. Negative 110.5 kilojoules per mole. And then what else do we have? We have our 4 C's, but remember, this is arbitrarily set as 0 like I mentioned earlier. So this is just going to be a 0 value. We don't really need to add it here. And then we have our 7H2O. So I'm going to multiply by, now we have 7 moles of it, of H2O. And we're just going to look for H2O. This is a liquid. So where is H2O liquid? On this chart. And it's right over there, negative 285.8. Kilojoules per mole. And then all of this here are just for the products. I need to do the same thing for my reactants, subtracted by our C6H14. Do we have that? Yes, we do. In the question it says that the standard molar enthalpy of formation of that is negative 198.7. So I'm just going to put negative 198.7 kilojoules per mole. But do not forget the amount of moles in question for C6H14. There is only 1 of it, so I have to multiply by 1 mole. All we're going to do, add this up, then subtract it by this, and you should get your answer. I ended up getting negative 2,305.9 kilojoules. I just leave it as kilojoules because, of course, all of these moles canceled out throughout the process of the calculation. Now, the question is also, remember, asking for the amount of energy lost per mole of C6H14 when combustion is incomplete. So we have the reference of what it would have been if it was a complete combustion. It would have been 4163. So it would have been this value. However, because we ended up doing it this way, doing it incomplete, we wasted a lot of energy. It wasn't done the most efficient way possible. So all we need to do is get our same number over there and then just find the difference between the two, and then you should get your answer. So I end up getting the answer of 1,857.3. This is the amount of kilojoules lost. Or let's try this question. We have ethanol written over here, and it's reacting with our acetic acid, right? Our acetic acid is over here, and it's producing ethyl ethanoate. Okay, it's something that's used to make polyurethane. I know it's not written in the question, but water is also produced, right? It's not written here, but it is a product over there. And what's a little bit interesting is that this thermochemical equation isn't necessarily complete because there is no value, our enthalpy value, that's usually written on the side. But in our question, if we keep reading on further, it says that there is 43 kilojoules. If this 43 kilojoules is a negative value, it should be placed over here. If it's a positive value, it should be placed over here. If it's just supposed to be written as a delta H value, then it should, if it's a negative value, it should be negative 43. If it's a positive value, it should just be plus 43. But nothing was written here on the side. So what can we assume? Well, the only thing we can assume is that because it's a positive value written in the question, that it is endothermic. So it must be 43 kilojoules. Okay, just a positive value. So let's write that in our formula. Let's first write it out. And let's input our 43 kilojoules in there. And then we have to get our delta HF, the standard molar enthalpy of the products. Remember, this is molar, so we got to start off with our molar value here of our first product in question, and there is only 1 mole of it, so I'm just going to put 1 mole. I'm going to multiply it by our standard molar enthalpy of ethyl ethanoate. Well, I'm looking over here, and I don't see it, and I'm reading in the question here, I don't have it, then this has to be an unknown value. And the question even says at the very end, we have to calculate the enthalpy of formation of ethyl ethanoate anyway. So this for sure is our unknown value, so I'm just going to put delta HF of our ethyl ethanoate. So CH3COO C2H5. Okay, then we have to start adding it with our other product here, our H2O. So I'm going to add it with how many moles? I have 1 mole of that H2O. And our H2O, we can find it over here. It's written here, our liquid water. It's negative 285.8. I'm going to multiply it by negative 285.8 kilojoules. Now again, this is per mole of that. So we're done that for the products. Now I need to do my reactants over here. So I'm going to negative, because that's what's written over here. My first reactant, our ethanol. And our first ethanol here, we have 1 mole of it. And then we have to multiply it by its standard molar enthalpy. Well, as we can see, it is written there in our chart. It's negative 277.7. Okay, and this is kilojoules per mole of that. And then we also have to add it with our next reactant. There's 1 mole of it as well. And then it's not written over here, our acetic acid, but we can at least find it in the question at the very end here that it's negative 486 kilojoules. And that should be it. So all you need to do is cancel out your moles here, cancel out your moles here, cancel out your moles here, and then we have to find our unknown value. So let's start doing the calculations. I'm just going to write this out as we go along. So we have our 1 mole here multiplied by our unknown value that we're still trying to find. And then this is going to be subtracting our negative 285. I'm going to subtract it by the addition of these two things. I'm just going to quickly use my calculator. And I end up getting negative 763.7 kilojoules. Let's keep writing it out as we go along. And let's add these two together, and you get 477.9. So we have this one that is kind of in the way. We want this one to be isolated and alone. So if this one is a positive 477, the opposite would be just be negative 477. So then these cancel out. If you do this on the right side, you need to do it on the left side. So I'm just gonna add this one over here. You've got negative 477.9 kilojoules. Okay, so then we end up just getting negative 434. It's equal to our 1 mole times our unknown value of ethyl ethanoate. And right now it's multiplying by our unknowing 1 mole. I want this one by itself, so what's the opposite of times 1 mole? It is divide 1 mole. So I'm just going to cancel these out. If I do it on the right side over here, I need to do it on the left side, so I'm going to divide by 1 mole. So I should end up getting my total value here. So this is of ethyl ethanoate, and the total value is negative 434.9 kilojoules per mole. This is the answer. Alright, these are the 2 green questions of the day. Question 1, question 2. Please give this a try on your own. Pause the video, and I'll be giving you the answers shortly. This is the answer to the first question. This is the answer to the second question.